to start the recording. And my mouth is a little dry today, so forgive me if I end up coughing or needing to take a couple sips of water as we go along. Okay, cool. But today, instead of straying towards or sticking with the life sciences aspect that we have done for the last year or so that I've been teaching, we're going to be looking at a field called astrophysics. And we're looking at a very specific kind of subfield of astrophysics, if you will. And we're going to talk about finding life. Have any of you guys watched E.T. Extraterrestrial, the movie? Okay,
I've heard of it.
that movie might be a little bit old for you guys. What's up, Daniel?
I've heard of it.
Okay, cool. Yeah, it's a famous movie, but ET means extraterrestrial or outside of this Earth, or in other words, alien. Um, and so the center of this class will be kind of looking at how we find other planets outside of our solar system, and how we look for signs of life on other planets. I like your background, Lyndon. Very nice. And Lyndon's gone. Okay. Any questions before we get started, guys? Cool. Okay. So to start off, I'm going to talk about exoplanets. Okay. So everybody here knows what a planet is, right? Okay, great. Thumbs ups all around. Awesome. So we have in our solar system, we have planets like Mercury and we have planets like Jupiter. And then we have ideal planets like Earth, where Earth and other ideal planets can support life. Does anyone know why Mercury doesn't have life on it? Yes, Lena.
It's very hot.
Yes,
Like,
right. Mercury is very close to the sun. Is that what you're gonna say, Daniel?
Ed.
Daniel answered it, but yeah, it's too hot and it's too cold.
Yes. Mercury is incredibly close to the sun, and on the side that faces away from the sun, I do believe it gets pretty cold. Does anyone know why life doesn't exist on Jupiter? This question is a little harder.
Because
Yes, Lyndon, go ahead.
It's kind of like Jupiter's because it's like made out of gas. You can't stand on air.
Right. Jupiter is what we call a gas giant, as opposed to Earth that is made out of rock. Like Earth has a core, and it is solid. Jupiter is a gas giant, basically. And so it is difficult to live in an atmosphere where it is only kind of gas. And also Jupiter is like very far away from the sun, so water doesn't do very well on Jupiter, and life needs water, like liquid water, to survive. So that's just another thing. Lena or Daniel, I saw you guys had your hands raised. Did you guys have anything to add?
I'm sorry, can you please repeat?
Okay, yeah. So the reason why you can't live on Jupiter is because Jupiter is something we call a gas giant. Basically, it is made out of gases. And I mean, think about living in gas. That's not very feasible. And the other reason is that it's also very far away from the sun, so any kind of water would not do well there. It would probably freeze. Is that okay, Lena?
Yes, thank you.
Okay, yes, of course. Also, am I pronouncing your name right, Lena?
Yes.
Okay, cool. And Daniel, did you have any questions, comments, or concerns? I know you had your hand raised.
I didn't have my hand raised.
Okay, cool. Wait, okay. Maybe you had like the thumbs up thing, and I thought it was a hand raise. Okay, but exoplanets are defined as any planet outside of our solar system. It could be a planet in the Milky Way. Our solar system only consists of, like the planets that we're used to, like Earth, Mars, Mercury, Venus, Uranus, Saturn, Jupiter. Exoplanets are any planet that orbits a star outside of our solar system. The star within our solar system we call the sun, but the sun is also just a star that is special to us because our life depends on the sun. Okay, so when we go and look for exoplanets, to find signs of life on exoplanets, we have to look for three kind of things. And we consider these kinds of things to be a checklist of sorts. Everyone knows what a checklist is? Okay, I hope you guys know what a checklist is. Have you guys ever like gone shopping and you guys have like a shopping list and you check everything off? Okay, that's a checklist. Point is, okay, great. I got a thumbs up. Thank you. Point is, when we go to look for exoplanets that may be able to host life, because that's
Wait. So an exoplanet is something. Wait, what's an exoplanet?
right. An exoplanet is any planet outside of our solar system that orbits a star.
Oh,
Right. And we care about exoplanets, Daniel. And the reason why they're important is that if we can find an exoplanet that may possibly be able to host life, like it has liquid water, it is the perfect distance from the sun, it is not a gas giant, well, then we might be able to find signs of life on that exoplanet. And, finding intelligent life outside of Earth is always something that you good, Daniel?
yeah.
Okay, yes. But as I was saying, finding intelligent life outside of Earth is something that we as humans have always been very interested in because because an intelligent species wants to know if there are other intelligent species out there. Is that okay, Daniel?
I have a question.
Okay, yeah. What's your question?
Do you think there's ever actually going to be other life? 'Cause I don't think so.
Do I think in the universe that there is a planet suitable for hosting life?
Yeah.
I think it's possible. More than 50-50. I think maybe not within my lifetime or even your lifetime will we discover a planet that has life on it, but I think somewhere out there is a planet that has either the possibility of hosting life or has life on it. I mean, years ago, they found evidence of ancient water on Mars. Did you see that? There was an ancient waterbed that one of the Mars rovers found. It might have been Curiosity, I'm not sure. But that means that at one point liquid water flowed on Mars, which is kind of crazy to think about, right? Okay, but point is, my answer is I think it's likely that there is some other form of life out there. But I might also just be hopeful, right, Daniel? Maybe I want to believe that there is life out there because I believe in the probability of millions of stars and millions of exoplanets, and one of them has to have the right kind of environment. Is that okay, Daniel?
I heard they did find like a planet like very like Earth, but all the colors were like different or something.
All the colors are what?
Different.
All the colors are different, huh? That might be because of the atmosphere. That might be because of I don't know. Are you talking about like there's no grass, so it's not green? Is that what you're talking about?
No, like there is grass, but then the grass is like yellow.
Huh. Okay. If the grass is yellow, that means it's dying, which is probably not a good sign.
Okay. Then I don't know.
Okay. If you want to talk about that more after class, stay behind and we'll do a Google search about this planet that magically changes the colors of grass. Okay, but when we go to look for exoplanets, we're taking a look at this checklist. And the first thing we want to look at is orbit. Does everyone know what orbit is? Let me explain orbit. Okay, I'm getting some thumbs ups, but I'll still explain orbit. Orbit is the path that a planet takes around its star. Earth takes 365 days to orbit the sun because that's 1 year for us. Some planets take less than an hour. Okay, maybe I kind of made that up. I don't know a planet that takes less than an hour, but there are exoplanets out there that take like 29 hours to orbit their star. Right. And so the orbit is very dependent on how far the exoplanet is away from its star. And the farther away the exoplanet is from the star, hi Colby. I'm recording, so don't worry, you'll be able to watch the lesson. Today's class is a little bit different. We're doing astrophysics, Colby. Okay, Colby's excited. Basically, we're looking at ways to find exoplanets, which are planets outside of our solar system that can host life. In other words, I'm teaching you guys how to find aliens. Okay, sick. Okay, anyways.
I know what an exoplanet is.
Oh, okay, cool. Do you want to tell me?
Yeah. You just explained it.
Okay, yes.
Because my grandpa is a person who studies outer space.
An astronomer.
Yeah.
Yeah.
Yeah. So I know a lot about space, I guess.
Okay. Yes. Cool. I mean, if you ever want to jump in with something cool you want to say, feel free to. But the first thing we look at, Colby and assembled class, is we look at the orbit of the exoplanet, how far away the planet is from the sun or from the star it's orbiting, right? If we have a planet that is super close to the star, then it becomes a fiery, it just like completely burnt. It becomes Mercury. It is terrible to live on. It is way too hot and water evaporates instantly. However, if it's too far away, take like I'm thinking like Uranus or something, or one of Jupiter's moons, water freezes very quickly because it's so far away, and because it's so cold. And so life isn't capable of sustaining itself on planets that are too far away or too close to the sun. The second thing we want to look at is density. Does anyone know what density is? Density is a little bit of an advanced topic. Yes, Colby.
I think it was like it's dense or like
I know. I think I know.
Okay, what's up, Daniel?
I think it's more like how thick it is.
Okay, yeah, I think you're on the right track, Daniel.
was I muted?
No, you weren't.
Okay.
How about I ask you guys a question? Does anyone know why ice floats on water? Yes, Colby.
Oh, okay, because I thought it might have been buoyancy that I was talking about. So it's like how like it can like for example if it has low density, that means like it can like go in like water and not sink.
Right. So basically, density is a measure of how much mass is packed into one specific little unit of volume, for example. So let me give you guys an example. I have a okay, look, I have a Polaroid of my friends and I, okay? You guys might be too young to know what Polaroids are. And then I have my phone, right? Which one is more dense?
The picture?
Okay. Colby, do you want to weigh in?
Yeah, that's what I was gonna say.
Okay.
I mean the I think it's the wait more density means like it has like it's heavier, right? Or
More
like
density means it's more heavier in one like
yeah,
unit
okay,
volume.
okay.
Okay. So let's say I take
The phone.
yes, okay, yes. So the phone is actually more dense. If I put the phone on water, it'll sink. But if I put the photograph on water, it will probably float. I'm not sure, but I know the phone will definitely sink. I've seen phones fall in water. They sink. They're pretty dense. The photograph, however, is much more airy per se. It's much less dense. And so it floats much better on water. Okay. Does everyone have like a general concept understanding of density? Okay.
Yes.
You guys will spend a lot of time on density in the future. Density is very important. But okay. We look at density for exoplanets because of planets like Jupiter. Everyone knows that Jupiter is a gas giant, and if you didn't know that Jupiter is a gas giant, now you know that Jupiter is a gas giant. We don't really want to live on gas giants. That's not particularly a good idea. And so we want to find a planet with a similar density to Earth. Earth has water, Earth has dry land, Earth has atmospheric gases like oxygen that keep us alive. And so we want a planet that has a density similar to Earth, right? If we have a density like Jupiter, well, then that's unsuitable for human life, and likely unsuitable for many other forms of life. However, if we have an exoplanet that is similar to Earth in density, it has liquid water, which is great, and it has dry land, which is also great, and it has atmospheric gases like oxygen, then it's even better. Then we know that the density is suitable for life. Yes, Colby, is there something you want to add?
It also might have the like like aliens or some other life there.
Yes. Yes, it might have extraterrestrial life, it might have intelligent life. Um, of course, I'm sure there are planets that are suitable but don't have any sort of life form, simply because life isn't just willy-nilly. It takes a lot of things to go right for life to occur, and for especially intelligent life to occur.
Lawrence,
Yes, Daniel.
I heard most life comes from photosynthesis.
Yes. Okay. So the earliest the earliest I forget how the earliest forms of life on Earth sustain themselves. Either they ate each other or they photosynthesized. Let me go check. It has been years since I took freshman biology. So how did the earliest life forms create food for themselves? Okay. Right. Okay. So Daniel, you were actually right. The first kind of bacteria, which we call cyanobacteria, and the first life forms on Earth, they use photosynthesis to produce food for themselves. So yes, that is a correct statement. Is that all, Daniel?
Yeah.
Okay. Okay, cool. I have another question for you guys. Let's say we have Mercury, which is basically a big ball of rock floating in space. And then we have Jupiter, which is a gas giant. Which planet is more dense? Colby?
Mercury?
Yes, Mercury. Think about it like this. If you have like a rock and you have some air, which one is going to be heavier? Obviously the rock, right? And you guys will eventually learn that you will have to have the same volume of each material to be able to compare their densities. But with such big planets like Mercury and Jupiter, it is relatively safe to assume that Mercury is much more dense than Jupiter. Jupiter is made out of gas. Okay. Cool. Okay. And the last thing that we look at when we look for exoplanets are signs of life. We want to look for oxygen in the atmosphere of planets, right? Humans are severely dependent on oxygen. And many other life forms in the ecosystem and in the food chain depend on oxygen, right? I mean, mice breathe oxygen, and then the hawks that eat the mice breathe oxygen, and then the hawks are the apex predators, blah blah blah. Of course, plants and trees, they use carbon dioxide, but oxygen is very crucial to intelligent life such as us. There's like a whole debate on whether or not we're like humans are intelligent life species, but I'm gonna refer to ourselves as intelligent life for the time being. Okay. Quick water break. Okay, cool. Now we're going to talk about how we determine the orbits of stars. And this is where we get into the nitty-gritty. Colby's giving me a look. Okay, so this is where the stuff gets complicated. And if you guys have any questions, this is the part where you can also just jump in at any time and feel free to be like, Lawrence, I don't understand this. Please explain. I have some questions. Okay. Remember that we want to determine orbits because of the fact that the orbits will determine, how warm or how cold the exoplanet is. Traditionally, we would use pictures and we would use telescopes to try and determine orbits, right? We take a picture and we measure, right? In trillions of miles, of course, or millions or billions, depending on how far the distances are. But because these stars and these exoplanets are trillions of miles outside of Earth. Ooh, I have a little bit of a food stain on my sleeve. Great. Because they are so far away, we get to this point where taking photographs, and even with high precision telescopes, doesn't really work. If you guys look at this photo was taken with a very powerful NASA telescope. And this is a picture of a star, I'd say many light years away, but you guys can notice that there's absolutely nothing. Like you can't figure out anything from this picture. It's literally pixels. And this happens because the star is basically glaring out the planet next to it. So in reality, if I can get my little annotation guy here.
It bends light, right?
Sorry, what's up, Colby?
It bends light, right?
Yes, big planets will bend light around them. However, that's not really what's happening here. What's happening here is that the exoplanet is just like this tiny dot next to the massive sun or the massive star, sorry. And the glare of the star just kind of covers up the exoplanet. And so we can now see that taking pictures with the telescope doesn't really get us anywhere, right, guys? Right. I mean, if you guys are able to tell me anything about that star or that exoplanet based on that pixelated photo, I would write a recommendation letter for you to go to NASA right now. Okay, but obviously, okay, I can't zoom out for some reason. Oh no, that's not good. There we go. Okay, solid. And so obviously we can't really use this kind of photography. So we rely on something called the wobble method. Does anyone know what the wobble method is? It's okay. Okay. As Colby said, all planets, no matter how small, have a gravitational force. Every object has a gravitational force. That's one of like Newton's big laws. Everyone knows who Isaac Newton is. Yes, big guy. F equals ma. But the bigger the object is, the kind of greater the gravitational pull. And with something as dense as a black hole, it can actually pull in light. And so black holes have insane like gravitational fields. If you get near a black hole, you're not leaving, unfortunately. Which is why light doesn't escape black holes, which is why the photo of a black hole is so cool. For astronomers, of course. I'm more of a life sciences guy, but I can appreciate the awesomeness of that photo. But well, we have to. What's up, Colby?
In the black hole, you can't get out because it'll like it spins so fast it sucks you in, and then like while it goes smaller and smaller. So basically, you'll be like super long, and then you keep on going. So
Really?
yeah.
Yeah, I didn't know that. I'm not an expert on black holes. I just know they are very dense and they don't let anything escape. Lena, what's up?
I'm pretty sure that the process of you stretching into a long thin strip is spaghettification. Yes, it's a sleep.
Spaghettification.
Yes, if you don't believe me, search it.
Okay. Let's see. Spaghettification.
Spaghetti.
Spaghettification.
You
Okay.
turn-
Yeah. When falling towards a black hole, for an example, an object is stretched in the direction of the black hole and spaghettified. Okay. No, yes.
spaghetti.
Okay.
Because like spaghettis are like long.
Right, right. Okay, so the more you know, if you get too close to a black hole, you get stretched out and then you're spaghettified. Okay. Back to the wobble method. Oh God, we're running out of Zoom time. Oh goodness gracious.
Yeah, and I have to go in 1 minute.
Okay. Okay, that's not good. It's okay, Colby. This recording will be online. Basically, when we look at trying to find the orbit of exoplanets around the sun and the star and the exoplanet actually kind of orbit around a central center of mass. And you guys might think that suns or stars are fixed in space, but they're not actually fixed in space. Yes, Colby.
I have to go now.
Okay, I'm sorry, Colby.
Bye.
All right, enjoy your Thanksgiving. Bye, Colby.
Today's
Take
my
care.
birthday. Today's my birthday, so
Today's your birthday. Happy birthday, Colby. Are you 10 now?
yes.
Okay. Happy birthday, Colby. Okay. That's great. He's 10 now. Wow. Y'all grow up so fast. Anyways, what we see here is that the big star and the tiny exoplanet exert a sort of pull on each other, the same way that a black hole exerts a pull on light or anything that comes close to the black hole. And what happens is because these two objects in space are pulling on each other here, let me circle it, here and here, they orbit around this kind of central center of mass. And what happens is the star begins to wobble. It wobbles around that center of mass. And we can pick up those wobbles from here on Earth. We just need really sensitive equipment and really expensive equipment. But it's doable. We've done it. We've done it over and over and over thousands of times. And by detecting the wobble of the star, we can actually calculate using simple astrophysics. I've looked at the math. It's pretty difficult. Using simple astrophysics, we can determine how far away this exoplanet is, and we can also determine the size of the exoplanet. And size is very important to calculating density. Okay. Any questions on the wobble effect, guys? Okay. I hope that means there are no questions on the wobble effect. Using the wobble effect, we can figure out a Goldilocks zone for specific if this thing will cooperate with me, we can figure out a specific Goldilocks zone for all exoplanets that we can find. Let me clear my annotations here. Okay, cool. Annotations cleared. Once we find this Goldilocks zone, we'll be able to see that some exoplanets are too cold. They're too far away from their stars. And we can tell that from the wobble. And then if they're too close, well, then they'll be too hot. However, if they are just in the right Goldilocks zone, which is this blue ring around this yellow star, then we know they're habitable for life, and we call that the Goldilocks zone. Any questions, anybody? Okay, cool. Okay, let's see here. Okay, now we have to determine density for for objects that orbit stars or exoplanets. I'm not going to talk about radial velocity, and nor am I going to talk about the Doppler effect. If you guys want to hear about those, you guys are happy to stay after class, and I will talk to you about those. But the Doppler effect and radial velocity are likely topics that are a bit complicated for you guys. Okay. Now I'm going to talk about how to determine another way of determining the size of an exoplanet. Okay. Okay, so before we get started, I just want to remind everyone that this is determining density. And if you guys will recall, the kind of idea of density being how much mass an object has within a specific little volume that we predefine. Okay. One of the main ways we can calculate the size of an exoplanet is through something called the transit method. Everyone knows that an exoplanet orbits a sun. And regardless of the wobble, the planet will orbit and it will orbit and it will orbit. And also regardless of how long it takes the planet to orbit that star. There are stars and exoplanets positioned out there so that we can see when the exoplanet passes in front of the star. And as we're looking, it's almost like the planet eclipses the star, right? If you guys look here, this is Jupiter passing our own sun. And if this was the moon, then it would be a solar eclipse. But it's Jupiter, so it's not the moon. But this kind of eclipse idea is the foundation of the transit method. So when an exoplanet passes in front of a star, we can actually see that the brightness of the star dims. And it dims because the planet blocks some of the starlight. Jupiter blocks about 1% of the starlight from our sun, and Earth, being much smaller than Jupiter, blocks about 0.008% of the brightness, which is basically non-detectable. But we can detect when a planet as big as Jupiter passes in front of our own sun. And so when we apply that to exoplanets that are out there, we can see that there are planets that are transiting or eclipsing in front of their stars. And we can determine the size of that planet based on how much the brightness drops by. I have a question for you guys. If I have a really big planet, will the brightness dim more or will it dim less?
More.
Okay, yes, great job. Nice, Lyndon. Yes, the planet, the brightness of the star will dim more. And that's because the planet is simply just bigger. And that's another great way we can calculate the size of that planet. And with the mass of the planet that we can determine from the wobble effect, and with the size of the planet that we can determine from the transit method, we begin to see a kind of relationship that allows us to determine density. I should also mention up here that I have something I forgot to mention earlier, but the wobble effect allows us to figure out the mass of the exoplanet. So how many kilograms are in the exoplanet, and also the size of the exoplanet. And simply the transit method is just another way for us to determine the size of the planet. And with the mass and with the size or volume of the planet, we'll be able to determine, excuse me, we'll be able to determine the overall density. And if the density is suitable, like the density of Earth, well, then we have another thing we can check off on our list. However, if the planet is very, if the planet is not very dense, it has the density of a gas planet, well, then we know that it is similar to Jupiter in density. And then it becomes a planet that is not inhabitable because we don't like to live on gas. Okay, any questions, anybody? Okay, cool. We are running out of time and I want to be able to play a quick game kit with you guys. We will decide on what we want to play, but I'm just going to give you guys a sneak peek of what we'll be doing next class. This might look kind of difficult, but these are absorption spectrums and emission spectrums for different elements. And we will talk about spectrums in the next class, and we will talk about like black body radiation. So that's all coming up. I'm going to stop my screen share. And then those of you who want to play a game on GimKit, feel free to rejoin. And those of you who feel that you guys have been learning and don't necessarily need to play the game, well, then I hope you guys all have a good week and enjoy your Thanksgiving. Okay, everybody? All right. Bye, guys. I'll see you guys all back soon. Bye-bye.